All right, welcome back. We're going to be starting in Chapter 2, Thermodynamics, the first law of thermodynamics specifically. And so I hope everybody is caffeinated and ready to plug in and get after it. So starting off, what is thermodynamics and the conservation of energy? The branch of physical chemistry known as thermodynamics is concerned with the study of the transformation of energy and, in particular, the transformation of heat into work and vice versa. That concern might seem remote from chemistry. Thermodynamics was originally formulated by physicists and engineers. However, thermodynamics has proved to be of immense importance in chemistry. Not only does it deal with the energy output of chemical reactions, but it also helps to answer questions that lie right at the subject's heart, such as why reactions reach equilibrium, their composition at equilibrium, and how reactions in electrochemical and biological cells can be used to generate electricity. Chemical thermodynamics is a tree with many branches. Thermochemistry is the branch that deals with the heat output of chemical reactions. As we elaborate the contents of thermodynamics, we'll see that we can also discuss the output of energy in the form of work. This connection leads us into the fields of electrochemistry, the interaction between electricity and chemistry, and bioenergetics, the deployment of energy in living organisms. The whole of equilibrium chemistry, the formulation of equilibrium constants, and the very special case of the equilibrium composition of solutions of acids and bases are all aspects of thermodynamics. Almost every argument and explanation in chemistry boils down to a consideration of some aspect of single property, energy. Energy determines what molecules may form, what reactions may occur, how fast they may occur, and, with a refinement in our conception of energy that we're going to deal with in Chapter 4, in which direction a reaction has a tendency to occur. So, let's lay down some fundamental definitions. Energy is capacity to do work. And work is done to achieve motion against an opposing force. So these definitions imply that a raised weight of a given mass has more energy than one of the same mass resting on the ground because the former has a greater capacity to do work. It can do work as it falls to the level of the lower weight. The definition also implies that a gas at a higher temperature has more energy than the same gas at a lower temperature. The hot gas has a higher pressure and can do more work in driving out a piston. People struggled for centuries to create energy from nothing, believing that if they could create energy, that they would be able to produce work and therefore wealth endlessly. However, without exception, despite strenuous efforts, many of which degenerated into deceit, they failed. As a result of their failed efforts, we have come to recognize that energy can be neither created nor destroyed, but merely converted from one form into another, or moved from place to place. This law of conservation of energy is of great importance in chemistry. Most chemical reactions release energy or absorb it as they occur. So, according to the law of conservation of energy, we can be confident that all such changes must result only in the conversion of energy from one form into another, or its transfer from place to place, not its creation or annihilation. The detailed study of that conversion and transfer is the domain of thermodynamics. So before we move on, I want to bring your attention to this center graph figure. And it's just something we've looked at ever since starting 100-level chemistry, where on the y-axis we have energy, and on the x-axis we have the reaction coordinate or progress of the reaction. And without getting into too many details, I just want to reiterate, if we think of energy in chemical reactions in contexts that we have intuition for. If this was a hill, a physical hill, and we had a ball at the top of the physical hill, sitting where B is, it would have a lot of potential energy that could be realized as it rolled down the hill to this low position. When we think of chemical energy, we can think of it in the same way. If we have a high energy intermediate or a transition state that resides at B, and we have reactants at A, and we have potential product at C, the relative energy levels are important because in chemistry, and this is something I'll probably refer to over and over again, energy has to do with stability. High energy systems are inherently less stable / less happy. Lower energy systems are inherently more stable or more happy. And we're going to see that trend where, in the case of this favorable reactions illustrated, reactant A goes to product C invariably because C is lower in energy and therefore more stable. Now, one other thing to recognize when we're looking at this that will likely come up throughout the rest of this book in different forms is that when we're evaluating equilibrium and rate, those are two different processes, and the equilibrium of the reaction is going to be determined by this blue arrow here that I'm circling, the difference in energy level between reactants and products. The rate of the reaction, the speed at which it can reach that new equilibrium, is determined by our red arrow, because that is how rapidly at a particular energy level we can overcome the energetic barrier between A and B so that it can go to C. Moving on to system and surroundings. In thermodynamics, a system is the part of the world in which we have particular interest. The surroundings are where we make our observations, and we can see this illustrated in figure 2.1 over here, which I'm struggling to use my pen for. There we go. Where you can see the system is what we're paying attention to, and the surroundings is everything around it. In this particular figure, the surroundings, which can be modeled as just a very, very large water bath, remain at constant temperature regardless of how much energy flows into or out of them. They're so huge that they also have either constant volume or constant pressure, regardless of any changes that take place to the system. Therefore, even though the system might expand, the surroundings remain effectively the same size. So we need to distinguish now between three different fundamental types of systems. There's open systems, closed systems, and isolated systems. An open system can exchange both energy and matter with its surroundings. A closed system can exchange energy but not matter with its surroundings. And an isolated system can exchange neither matter nor energy with its surroundings. So an example of an open system is a flask that is not stoppered and to which various substances can be added. So a biological cell is an example of an open system because nutrients and waste can pass through the cell wall. You and I are open systems. We ingest, respire, perspire, etc. An example of a closed system is a stoppered flask. Energy can be exchanged with the contents of the flask because the walls may be able to conduct heat, but there's no physical exchange of matter with the surroundings. And an example of an isolated system is a sealed flask that's thermally, mechanically, and electrically insulated from its surroundings, preventing the exchange of both matter and energy with the surroundings. and moving along to work and heat. Energy can be exchanged between a closed system and its surroundings by doing work or by the process called heating. A system does work when it causes motion against an opposing force, where work equals force times distance. We can identify when a system does work by noting whether the process can be used to change the height of a weight somewhere in the surroundings. Heating is the process of transferring energy as a result of a temperature difference between the system and its surroundings. So, to avoid a lot of awkward circumlocution, it's common to say energy is transferred as work when the system does work, and energy is transferred as heat when the system heats or is heated by its surroundings. However, we should always remember that work and heat are modes of transfer of energy, not forms of energy. Very important distinction. Although in everyday language the terms temperature and heat are fundamentally used synonymously, they're entirely different entities. Heat, Q, is energy in transit as a result of a temperature difference. Temperature, T, is an intensive property that is used to define the state of a system and determines the direction in which energy flows as heat. So, very important distinctions. Walls that permit heating as a mode of transfer of energy are called diathermic, and we can see this illustrated below in 2.4. So a metal container is diathermic. Walls that do not permit heating, even though there's a difference in temperature, are called adiabatic. A good example of an adiabatic system would be a double-walled flask which contains a vacuum between the two walls. And it's not a perfect adiabat, but it's a reasonable approximation. Later in the text, we'll discuss the molecular interpretation of temperature. At this stage, all we need to appreciate is that the temperature is the single parameter that tells us the relative populations of the available energy levels in a system. We need to recall from the introductory chemistry courses that we've had that molecules can possess only certain energies, quantized quantities of energies. At any given temperature, the number of molecules that occupy the available energy levels depend on the temperature. At low temperatures, most molecules are in the lowest energy states. As the temperature is increased, more molecules occupy states of higher energy, so the population spreads into these upper states, as we see illustrated in figure 2.3. And it's temperature that is the parameter that summarizes this spread of populations. So in 2.3 here we see that the temperature is a parameter that indicates the extent to which the exponentially decaying Boltzmann's distribution reaches up into the higher energy levels of the system. In A, we see when the temperature is low, only the lower energy states are occupied. But in B, at higher temperatures, more higher energy states are occupied. In each case, the populations decay exponentially with increasing temperature, with the total populations of all levels constant. So, taking a little step back to the transfer of energy, as an example of the different ways of transferring energy, consider a chemical reaction that produces gases, such as the reaction of zinc with an acid. So in this particular case, here we have solid zinc, single equivalent, reacts with two equivalents of hydrochloric aqueous acid, resulting in the formation of zinc chloride in the aqueous phase plus hydrogen gas. Suppose first that the reaction takes place inside a cylinder fitted with a piston. Then the gas produced drives out the piston and raises a weight on the surroundings. So this is illustrated over here in figure 2.5, where we can see that here we have a vial of hydrochloric acid and a piece of metallic zinc, and when we mix the two, as an outcome, we produce hydrogen gas, which causes an expansive force driving upwards on the piston. In this case, energy has migrated to the surroundings as a result of the system doing work because a weight has been raised in the surroundings. That weight can now do more work, so it possesses more energy. Some energy also migrates into the surroundings as heat. We can detect that transfer of energy by immersing the reaction vessel in an ice bath and noticing how much ice melts. Alternatively, we could let the same reaction take place in a vessel with a piston locked in position without the ability for it to move. In that particular case, because work equals force times distance, and because if no distance is traveled, no actual work is performed, no work is done because the weight is not raised. However, because it is found that more ice melts than in the first experiment, we can conclude that more energy is migrated to the surroundings as heat. A process in a system that releases energy as heat is called exothermic. A process in a system that absorbs energy as heat is called endothermic. An example of an exothermic reaction is any combustion of an organic compound. Endothermic reactions are much less common. The endothermic dissolution of ammonium nitrate in water is a classic example, and it's the basis of the instant cold packs that are included in first aid kits, and as well as just becoming handy if you're working outside in Alaska and want to keep your hands warm. They consist of a plastic envelope containing water, dyed blue for psychological reasons, saying that it's cold, and a small tube of ammonium nitrate, which is broken when the pack is used. The clue to the molecular nature of work comes from thinking about the motion of a weight in terms of its component atoms. When a weight is raised, all its atoms move in the same direction. This observation suggests that work is the mode of transfer of energy that achieves or utilizes uniform motion in its surroundings, and we see this in figure 2.6 over here. Whenever we think of work, we can always think of it in terms of uniform motion of some kind. Electrical work, for instance, corresponds to electrons being pushed in the same direction through a circuit. Mechanical work corresponds to atoms being pushed in the same direction against an opposing force. Now consider the molecular nature of heat. When energy is transferred as heat to the surroundings, the atoms and molecules oscillate more vigorously around their position or move more rapidly from place to place. The key point is that the motion stimulated by the arrival of energy from the system as heat is disorderly, not uniform as in the case of doing work. This observation suggests that heat is the mode of transfer of energy that achieves or utilizes disorderly motion in the surroundings, and that's what we're seeing illustrated in figure 2.7 over here to the right. A fuel burning, for example, generates disorderly molecular motion in its vicinity. It's a good example of heat versus classic work. An interesting historical point is that the molecular difference between work and heat correlates with the chronological order of their application. The release of energy when a fire burns is a relatively unsophisticated procedure because the energy emerges in a disordered fashion from the burning fuel. It was developed early in the history of civilization and generally taken for granted because of that. The generation of work by a burning fuel, in contrast, relies on carefully controlling the transfer of energy so the vast number of molecules move in unison. Apart from nature's achievement of work through the evolution of muscles, the large-scale transfer of energy by doing work was achieved thousands of years later than the transfer of energy by heating, as it had to wait for the development of the steam engine. So, since we've been talking about work, let's talk about the actual measurement of work. We saw in the review at the beginning of the book, or in our prerequisite physics courses, that the force opposing the raising of mass m vertically on a surface of Earth is mass times gravity, where g is the acceleration of free fall, 9.81 meters per second squared. Therefore, the work done to raise the mass to a height h is equal to mass times acceleration due to gravity times height h, mgh. It follows, I'll give you a little note here. It follows that we have a simple way of measuring the work done by or on a system. We measure the height through which a weight is raised or lowered in the surroundings, and then use equation 2.1. When a system does work, such as by raising a weight in the surroundings or forcing an electric current through a circuit, the energy transferred, W, is reported as a negative quantity. For instance, if a system raises a weight in the surroundings and in the process does 100 joules of work, that is, 100 joules of energy leaves the system by doing work, then we write W equals negative 100 joules. When work is done on the system, for example, when we wind a spring inside a clockwork mechanism, W is reported as a positive quantity. We write W equals plus 100 joules to signify that 100 joules of work has been done on the system. That is, 100 joules of energy has been transferred to the system by doing work. The sign convention is easy to follow if we think of changes to the energy of the system. Its energy decreases, W is negative, if energy leaves it. And its energy increases, W is positive, if energy enters it. Another way to think about this is to always remember that whenever we're thinking of delta, delta is determined by final quantity minus initial quantity. So delta of any quantity is going to be determined by its final state minus the initial state. This helps solidify in your minds that if the final state is lower than the initial state, you're going to have a negative quantity, and if it's higher than the initial state, it will be a positive quantity. We use the same convention for energy transferred as heat, Q. We write Q equals negative 100 joules if 100 joules of energy leaves a system as heat, so reducing the energy of the system, and Q equals plus 100 joules if 100 joules of energy enters the system as heat. Because many chemical reactions produce gas, one very important type of work in chemistry is expansion work. The work done when a system expands against an opposing pressure. The action of acid on zinc, which we saw on previous slides in figure 2.5, is an example of a reaction in which expansion work is done in the process of making room for the gaseous product, in this particular case hydrogen. When a system expands through a volume, delta V, against a constant external pressure, the work done is equal to equation 2.2. W equals negative pressure external times the delta V for the swept volume of the expansion. And this particular equation does have a derivation that's in the textbook that I'm not going to discuss. So according to this equation 2.2, the external pressure determines how much work a system does when it expands through a given volume. The greater the external pressure, the greater the opposing force, and the greater the work that a system does. When the external pressure is zero, work is inherently zero as well. In this case, the system does no work as it expands because it has nothing to push against. Expansion against zero external pressure is called free expansion. So, From the previous slide, equation 2.2 shows us how we get the least expansion work from a system. We just reduce the external pressure to zero. But how can we achieve the greatest work for a given change in volume? According to 2.2, the system does maximum work when the external pressure has a maximum value. The force opposing the expansion is then the greatest, and the system must exert more effort to push the piston out. However, that external pressure cannot be greater than the pressure P of the gas inside the system, for otherwise the external pressure would compress the gases instead of allowing it to expand. Therefore, maximum work is obtained when the external pressure is only infinitesimally less than the pressure of the gas in the system. In effect, the two pressures must be adjusted to be the same at all stages of the expansion. In the introduction, we called this balance of pressures a state of mechanical equilibrium. Therefore, we can conclude that a system that remains in mechanical equilibrium with its surroundings at all stages of the expansion does maximum expansion work. There's another way of expressing this condition. Because the external pressure is infinitesimally less than the pressure of the gas at some stage of the expansion, the piston moves out. However, suppose we increase the external pressure so that it became infinitesimally greater than the pressure of the gas. Now the system's piston moves in. That is, when a system is in a state of mechanical equilibrium, an infinitesimal change in the pressure results in opposite direction of motion. A process that can be reversed by an infinitesimal change in a variable, in this case the pressure, is said to be reversible. In everyday life, reversible means a process can be reversed. In thermodynamics, it has a stronger, more specific meaning. It means that a process can be reversed by an infinitesimal modification in some variable, in this case pressure. We can summarize this discussion by the following remarks. First, a system does maximum expansion work when the external pressure is equal to that of the system at every stage of the expansion, where P expansion equals pressure. Secondly, a system does maximum expansion work when it is in mechanical equilibrium with its surroundings at every stage of the expansion. And thirdly, maximum expansion work is achieved in a reversible change. All three statements are fundamentally equivalent, but they reflect different degrees of sophistication in the way the point's expressed. We cannot write down the expression for maximum expansion work simply by replacing P external in equation 2.2 by P, the pressure that's inside the gas cylinder, because as the piston moves out, the pressure inside the system falls. To make sure the entire process occurs reversibly, we have to adjust the external pressure to match the changing internal pressure. Suppose that we conduct the expansion isothermally, meaning at a constant temperature, by immersing the system in a water bath held at a specific temperature. As we show in the derivation previously in the book, if you want to go back to it, the work of isothermal reversible expansion of a perfect gas from an initial volume V initial to final volume V final at a given temperature T is given by equation 2.3, where work equals negative nRT times the natural log of final volume over initial volume, where n is the amount of gas molecules in the system. This results is equal to the area beneath the graph of P equals nRT over V between the limits of initial volume and final volume that we see in figure 10. And if we take a look at figure 2.10 here, the work, and on the y-axis we're seeing our pressure, on the x-axis we're seeing volume, and we have 2 points that we're evaluating between our initial volume and our final volume for the expansion. the work of reversible isothermal expansion of a gas is equal to the area underneath the corresponding isotherm, evaluated between the initial and final volumes, which are, in this case, colored yellow. The isotherm shown here is that of a perfect gas, but the same could be true of any gas, including real gases. So, moving along to the measurement of heat. When a substance is heated, its temperature typically rises. We say typically because the temperature does not always rise. The temperature of boiling water, for instance, remains unchanged as it's heated because it goes through a phase change going to steam. But we'll get into that more with phase changes and the energy invested in phase changes in Chapter 5. For a specified energy Q transferred by heating, the size of the resulting temperature change, delta T, depends on the heat capacity of the substance. Heat capacity, C, is defined as Q over delta T, or the energy supplied as heat over the change in temperature. What we can think of this as is how much heat does a particular substance require to increase a unit of temperature. And that varies from substance to substance based on its chemical properties. For instance, water has a fairly high specific heat. It takes quite a bit of energy to heat a gram of water 1 degree Celsius, whereas by comparison, metals will require substantially less thermal energy per gram of metal to heat it 1 degree Celsius. So it follows that we have a simple way of measuring heat absorbed or released by a system. We simply measure a temperature change and then use the appropriate value of the heat capacity of the system. And this gives us equation 2,4b, which is just a simple rearrangement of the above equation, where Q now equals heat capacity times delta T. Heat capacities occur frequently in the following sections and chapters, and we need to be aware of their properties and how their values are reported. First, we note that the heat capacity is an extensive property, meaning a property that depends on the amount of a substance in the sample. 2 kilograms of iron has twice the heat capacity of 1 kilogram of iron, so twice as much heat is required to raise its temperature by a given amount. It's more convenient to report the heat capacity of a substance as an intensive property, a property that's independent of the amount of substance example. We therefore use either the specific heat capacity, C sub S, which is my personal preference, which is the heat capacity divided by the mass of the sample, or the molar heat capacity, C sub M. The heat capacity divided by the amount of substance in moles, where C over N gives you your final value. In common usage, the specific heat capacity is often called specific heat. They're used interchangeably, and both are appropriate. To obtain the heat capacity of a sample of known mass, or that contains a known amount of substance, we use these definitions in the form C equals mass times C sub S, or C equals N times C sub M, respectively. For reasons that we're going to explain soon, the heat capacity of a substance depends on whether the sample is maintained at constant volume, like a gas in a sealed rigid vessel, as it's heated, or whether the sample is maintained at a constant pressure, like water in an open container, and free to change in volume. The latter is a more common arrangement, and the values given in a following table, table 2.1, are for heat capacity at constant pressures, C sub P. The heat capacity at constant volume is denoted as C sub V. The respective molar values are denoted C sub PM and C sub VM. So I mentioned different substances have different heat capacities. The reason why different substances have different molar heat capacities can be traced to differences in the separation of their energy levels. We shall understand these differences when we start quantum theory in second semester physical chemistry. But as we remarked earlier from introductory chemistry courses, we know that molecules can exist with only certain energies. If these energy levels are close together, the incoming energy can be accommodated with little change in their populations. The change in temperature, which determines the populations, is therefore also small, and the heat capacity is correspondingly large. In other words, closely spaced energy levels correlate with a high heat capacity. The translational energy levels of molecules in a gas are very close together, and all monatomic gases have similar molar heat capacities. The separation of the vibrational energy of atoms bound together in solids depends on the stiffness of the bonds between them and on the masses of the atoms, and solids show a wide range of molar heat capacities. So, if you stick with chemistry and physical chemistry, particularly into second semester, we'll learn a lot more about these subpopulations and distributions later on. Now, moving back, one way to measure the energy transferred as heat in a process is to use a calorimeter, which is displayed in figure 2.14 over here, which consists of simply a container in which the reaction or physical process occurs, a thermometer, and a surrounding water bath. The entire assembly is insulated from the rest of the world. The principle of a calorimeter is to use the rise in temperature to determine the energy released as heat by the process occurring inside it. To interpret the rise in temperature, we must first calibrate the calorimeter by comparing the observed change in temperature with a change in temperature brought about by the transfer of a known quantity of an energy as heat. One procedure is to heat the calorimeter electrically by passing a known current for a measured amount of time through a heater and record the increase in temperature. The energy provided electrically is Q equals IVT, where I is the current in amperes, V is the potential in of the supply in volts, and T is the time for which the current's flowing. So you have your current, your voltage, and your time. The observed rise in temperature lets us calculate the heat capacity of the calorimeter, which is is also called the calorimeter constant, from equation 2.4. Then we use this heat capacity to interpret a temperature rise due to a reaction in terms of the heat released or absorbed. An alternative procedure is to calibrate the calorimeter by using a reaction of known heat output, such as combustion of benzoic acid, which is well defined, where the heat output is 3,227 kilojoules per mole of benzoic acid consumed. Just because it's worth slowing down the theory, I'd like to run through an example here of calibrating a calorimeter and measuring its heat transfer with example 2.1. In an experiment to measure the heat released by the combustion of a sample of nutrient, the compound was burned in a calorimeter and the temperature rose by 3.22 degrees Celsius. When a current of 1.23 amps from a 12.0 volt source flows through a heater in the same calorimeter for 156 seconds, the temperature rose by 4.47 degrees Celsius. What is the heat released by the combustion reaction? So the overall strategy for problem solving here, we calculate the heat supplied by the electrically through equation 2.5, and 1 amp volt second equals 1 joule. Then we use the observed rise in temperature to find the heat capacity of the calorimeter. Finally, we use the heat capacity to convert the temperature rise observed for the combustion into a heat output by writing Q equals C delta T, and we solve. So in the solution, first we need to look at the energy provided electrically. Q equals the amps times the volts times the time in seconds. So 1.23 amps times 12 volts times 156 seconds gives us 156 joules. Excuse me. 156 amp volt seconds equals 156 joules. So this product works out to 2.30 kilojoules, but to avoid rounding errors, we save the numeric work for the final stage. The heat capacity of the calorimeter is therefore C equals Q over delta in temperature. So what we see is this quantity Q substituted here divided by 4.47 degrees Celsius, and that gives us a final quantity of C being 515 joules per degree Celsius for the entire calorimeter. But we don't evaluate it yet in the actual calculation. So the heat output of the combustion of the chemical in question is therefore Q equals C times delta T, and is therefore 1.66 kilojoules. In certain cases, we can relate the value of Q to the change in volume of a system, and so can calculate, for instance, the flow of energy as heat into the system when a gas expands. The simplest case is that of a perfect gas undergoing isothermal expansion. We can use a molecular interpretation to guide our thoughts. Because the expansion is isothermal, the temperature of the gas is the same at the end of the expansion as it was initially. Therefore, the mean speed of the molecules of the gas is the same before and after the expansion. That implies, in turn, that the total kinetic energy of the molecules is the same. But for a perfect gas, the only contribution to the energy is the kinetic energy of the molecules. So we have to conclude that the total energy of the gas is the same before and after the expansion. Energy has left the system as work. Therefore, a compensating amount of energy must have entered the system as heat. We can therefore write, for the isothermal expansion of a perfect gas, Q must equal the negative quantity of the magnitude of work. For instance, if we find that W equals negative 100 joules for a particular expansion, isothermal expansion, meaning that 100 joules left the system as a result of the system doing work, then we can conclude that Q must equal plus 100 joules, meaning 100 joules must enter as heat. For free expansion, work equals 0, because there's no force opposing it. So we conclude that Q must therefore equal 0 as well. There's no influx of energy as heat when a perfect gas expands against 0 pressure. If the isothermal expansion is also reversible, we can use equation 2.3 for the work in equation 2.6 and write the following. For the isothermal reversible expansion of a perfect gas, Q equals nRT times the natural log of the final volume over the initial volume. We interpret this expression as follows. 3 points. Firstly, when the final volume is greater than the initial volume, as in an expansion, the logarithm is positive, and we conclude that Q must be greater than 0. as expected. So Q flows as heat into the system to make up for the energy being lost as work. Second point, the greater the ratio of the final and initial volumes, the greater the influx of energy as heat. That makes sense. And thirdly, the higher the temperature, the greater the quantity of heat that must enter for a given change in volume. We've seen that more work is done at higher temperature, so more heat must enter to make up for the energy lost. And that's going to be it for this lecture. In the next lecture, we're going to pick up right here and wrap up the chapter. But go ahead and take a break, get another cup of coffee, and then maybe plug back into round 2.